Hi, so this example is going to illustrate the cracked moment of inertia for a growth section and a transform section. So this is going to be based on problem 4.2, and what you need is to find the moment when the concrete will crack. What we know are the section properties, the material properties, and the equation of moment as a function of stress. So you know that stress is equal to my I. So for a crack section, for finding the cracking moment, we want to set the stress equal to the rupture stress, which for this problem we're going to use 7.5 is times square root F prime C, and F prime C is in PSI. For this problem, F prime C is 5,000 PSI, so that your rupture stress is equal to 530 PSI. And note here that our rupture stress is approximately equal to a tenth of the compressive stress. So this problem, we wanted to know the cracking moment for gross section properties and for transform section properties. So the first part, we're going to do just the gross section. And for the gross section, it's just the gross section modulus. So you know this is equal to 1/12 base times height cubed. And if we rearrange this, this is equal to to solve for our M cracking, our cracking moment then is equal to our rupture stress times the gross moment of inertia over Y, which is the distance from the neutral axis to the extreme tension fiber. Setting that all equal, solving for our moment of inertia, our gross moment of inertia is 1/12 base times height. 1/12 times 12 inches times 36 cubed gives us 46,656 inches to the fourth. Y for our gross section is just h over 2, since the neutral axis is at half the depth, so our y is equal to 18, and our cracking moment then comes out to be 114 kip feet. Make sure that you keep track of your units. It starts out in 530 psi, so we're in pounds per square inch times inches to the fourth over inches leaves us with pound inches. Convert to feet and kips. So our cracking moment using our gross section properties is equal to essentially 115 kip feet. Now looking at part 2 for our transform section, what we want to do is consider the contribution of steel to the cracking moment. Note, previously we just did the gross section, so we just completely neglected any contribution from the steel. So if we're basing our calculation off the concrete tensile strength, we need to convert the steel to equivalent concrete area. So with our neutral axis, we need to find what our neutral axis is. So we're going to transform the area of steel to an equivalent amount of concrete. So this is equal to N times the area of bars. In this problem, we have two number 10 bars. The area of those is equal to 1.27. So 2 of those gives us an area of 2.54 inches to the squared. And our transformed area then of steel is N times AS. So it's 7.2 times 2.54, which comes out to be 18.3 inches squared. Note our N is just equal to ES over EC, and the EC was equal to the equation 57,000 times square root F prime C. And because you have ES over EC, these are both units of force per area, so it ends up being a unitless value. Now, the whole problem of visualizing this transform section. The steel, the way that we visualize this is that we extrude this steel horizontally so as not to change its distance from the neutral axis. What we do is we keep the height of the extruded section constant. To visualize this, let's say that the height of the section is going to be equal to the diameter of the bars. So those bar diameters are equal to, if it's a number 10, it's 10 over 8, because it's over 8 for all of those. That gives us 1.25 inches. That's the diameter of a number 10 bar. we're considering all the contributing area as concrete. Therefore, when we look at just this concrete section and we take out these bar areas, this is the gross section area minus the area of 2 bars. So our area of concrete is AG minus AS. And we say that the total area then, when we consider the transform section, is the total area of concrete minus the area of the 2 bars, because that's occupied by steel. But if we're transforming that steel area, we have area of steel transformed such that our total area is equal to the area of concrete, which we said was AG minus the 2 bar areas, plus the area of transformed steel. So if we want to just use the AG, what we say is, to make our calculations easy, we use the gross section, the gross concrete area, plus the area of the transformed steel, which is this guy, AS times N, and then we subtract, we just move this guy over, AS. So this is where the equation, the gross area plus the area of steel times N minus 1 comes from. So now if we want to look at this, let's imagine that we're using 2.4 inches squared of that area. Let's put a square on there. So use 2.54 inches squared of the transformed steel to fill the holes, and then use AG. So the area of the extruded, so all we're saying is what is the dimension of this? I know everybody's been having a hard time visualizing this. So what is the dimension of this? If we say that we're just going to use a height equivalent to the bar diameter, we're going to figure out how far this extrudes out. So we have our total area of an extruded section, so it's the total transformed area minus that 2.54 square inches that we're using to fill the holes so that we can use AG. Then this gives us a distance extending from the block equal to 12, if this is our square area of transform section that's left over after we fill the 2 holes, then we have 15.75 inches squared divided by the height, so that we're extruding 12.6 inches total out of the concrete block. So if we put half of this on each side, then we have 6.3 inches extruding this way, 6.3 inches extruding this way, and both of them are a height of 1.25 inches, which is the bar diameter. So now we're taking a look at this section, and we're going to find our transform section. So the first thing we need to do is find the neutral axis of this transform section. We want to find our I transform, the transform moment of inertia of this guy. Our concrete section, we're using our gross, remember, so this is the 432, and then we're using the distance from the bottom, using this Y. This is going to be our Y bar. The Y distances for the concrete gross section is 18, because this was a 36-inch section. And then our transform steel is 2.5 inches from here. Our area, so this area is what's left, this 15.75 multiplied by Y gives us 39.375. The gross section area times its distance to its neutral axis from the bottom is 7776. So that our total area comes out to be 448 essentially, and the AY is 7815 inches cubed. So to get our neutral axis of that transform section, we divide the sum of the areas times the distance to their neutral axes, divide by the total area, and then we have a neutral axis located of the transform section at 17.45 inches from the bottom. So after that, what we can do now is use a parallel axis to find the transform moment of inertia. So recall that our transform moment of inertia is going to be equal to the sum of the individual, the respective moment of inertia of each section about its own neutral axis, plus its area times its distance squared from the composite, the transform section neutral axis. So that's this D. So this D is equal to the individual distance to its individual moment neutral axis minus the transform neutral axis distance. So if we look at our steel, our transform steel, one of these, remember this is 6. Let me change this. I'm getting pretty good at this. Let's cut that. And now we want to say that this is the 6.3. Oops. Okay, so that's 6.3 inches, and our height is the 1.25 inches. So our moment of inertia of this section, there's going to be 2 of them, but the first one is, we just do 1/12 base times height cubed. So 1/12 base is the 6.3, the height is the bar diameter 1.25 cubed, so that comes out to be 1 inch squared, essentially, for each of these. So when we look at our moment of inertia about its own neutral axis, the total is going to be 2.05. And notice that the gross for the concrete section is just the moment of inertia of the gross section. That's what we used from part 1. So our total moment of inertia about their own neutral axis are equal to 46,658. Then we want to take the distance squared times the area from the transform section neutral axis. So the distance times the distance of the neutral axis from this to the transform section neutral axis is just the total transform section neutral axis from the bottom minus this. If we keep the units or the signs consistent, that doesn't really matter if this is negative because it's going to end up squared over here. So looking at the components of what make up our transform section neutral axis is the gross and the transform steel moment of inertia is about their individual respective axes, and then each of their individual areas times the distance that the individual neutral axis is from the transform neutral axis. So for the concrete section, it's only 0.55 inches from the neutral axis. We square that, that gives us a teeny little number here, but this guy is really big, and so this is where the contribution of the steel comes from. It gives us 3,520 inches squared. So these 4 components, this one, this one, this one, and this one, are all our comprise our transform neutral axis, our transform moment of inertia. So notice how small the transform steel's own moment of inertia is. So that's why we're always neglecting it. So it makes sense that when we do all of our equations, we usually just neglect this and we just take this AD squared. And this doesn't give us much either. So these are the 2 main components that contribute to the transform section neutral axis. So carrying that all out, we end up with a moment of inertia of the transform section equal to 50,309 inches to the 4th, and therefore we can just plug that into here, and make sure that you use your new transform neutral axis, which is 17.45, so that we have a cracking moment of the transform section equal to 127 kip feet. Now come back and compare that with the 115, let's just say. Let's write that in here. So that in cracking gross is equal to 115. Kip feet. So you can see that there's a whole lot of work for not a lot of difference. So if we were to compare our cracking moment, I want you to think about Is it going to be more or less conservative to use the transform section? So I'll let you think about that, and hopefully this was helpful to you.